right, the root of the problem, the number that cubes. A cube whose side lengths measure 1 unit has been dilated by several scale factors to make new cubes. For what scale factor will the volume of the dilated cube be 27 cubic units? So we're taking a cube, it's a 1 by 1 cube, 1 by 1 by 1, so the volume is 1 unit cubed. Now, if we have, so for number 1, we have our scale factor, cubed times our original volume, and that's 27. So what cubed equals 27? It's 3, because the cubed root of 27 equals 3, or something times something times something, and the only thing that fits in there is 3. Okay? For what scale factor will the volume of the dilated cube be 1,000? Well, it's something raised to the 3rd power times the original volume is 1,000. Well, when I have 3 zeros, I actually know that if I multiply that 3 times, I get 1,000. 10 times 10 times 10 equals 1,000. And then 3. Estimate the scale factor. Okay, that one's a little harder. 1,001. Well, it's going to be a little bit more than 10, but we don't know. Okay, it's basically the cubed root of 1,001, which is harder to get to. .003. Okay, and then number 4, estimate the scale factor, cubic volume of 7. So it's something cubed times the original is 7. Okay, it's the cubed root of 7. It doesn't really matter what it really is. 1.9. Approximately 1.9. If I cube 1.9, I get close to 7. So thinking inside the box, a shipping company makes cubed-shaped boxes. Their basic box measures 1 foot per side. They want to know how to scale the basic box to build new boxes of various volumes. If the company wants a box with a volume of 8 cubic feet, by what scale factor do they need to dilate the box? So they want 8, the original is 1, times something cubed. Okay, so our scale factor is 2, because 2 cubed is 8. If they want a box with a volume of 10 cubic feet, approximately what scale factor? So our original times our scale factor cubed equals 10. Let's see. Approximately 2.15. Okay? The company decides to create a graph to help analyze the relationship. So what we're really doing is taking the cubed root of all these. Okay, so the cubed root is 0, 0. I can go 1. Here I can go 2. And here 3. Okay, in between, not quite as easy. But it's cubed root. Sorry, I forgot to draw that in. Okay, we can put decimals in there, but they're not very helpful because they're not exact numbers. So I can plot the points and connect them with a curve. And here is where I messed up last time in the last lesson. Volume is x and scale factor is y. So this is my x and that's my y. I'll be right back. All right, so I plotted the points and I did cubed roots because I don't want to put in any decimals that I have to round. The x-axis is the volume and the y-axis is the scale factor. And if we look right here, we see that we're modeled by a cubed root function. Okay, I can actually show you the whole thing because, yeah, we've got negatives, but we're ignoring those because I can't have negative volumes and scale factors. I can have, nope. but we just want to look at the positives. And this models our volume function. Okay, where are we going with this? So we're good. The graph shows the relationship between the volume of the dilated box and the scale factor. Write an equation that describes this relationship. Okay, that's just what we did. Y equals the cubed root of x. Okay, suppose that a company builds a box with a volume of 21 cubic feet and then decides to build another with a volume of 25 cubic feet. Use your graph to estimate how much the scale factor changes between these two dilated boxes. What was it, 28 and 25? I need to move that. And x equals 21 and 25, my bad. 21 and 25. Let's move this back over. So our scale factor is approximately 2.7 for the 21 cubic foot box and 2.9 for the other box. And graphically that's great, but you can also just take the square root or the cubed root of 21 and the cubed root of 25 and get the same answer. Use your graph to estimate how the scale factor changes between a box with a volume of 1 and a box of a volume with 5. Okay. There's our 1 and 5. It's already on the graph. And it's that cubed root function. Cool. All right. Satellite scale factors. A government agency is redesigning a satellite or an object that goes in orbit around the Earth. The surface of the satellite is covered with solar panels that supply the satellite with energy. The interior of the satellite is filled with scientific instruments. In the current design, the satellite has a surface area of 5.4 square feet and a volume of 1.2 cubic feet. If the agency wants to increase the surface area to 21.6 square feet so the satellite can generate more energy, by what scale factor do they need to dilate the satellite? All right, so we have surface area. We're doing 5.4, and we want it to be 21.6. So that got bigger. Let's go ahead and figure our scale factor. Okay, that gives me a number of 4, but that's not the scale factor. Remember, when we're dealing with volumes, scale factor is squared, so our scale factor is actually 2. Okay, if we try the volume, we're going from 1.2 to 5.04. Okay, that got bigger, so we want to divide this way. That gives us 3.375, but that's not it because it's volume, so I need to take the cube root of it. So that gives me a scale factor of 1.5. Okay, so our figure went from small to big. That means I need to do the division to get a number bigger than 1 and then take the square root of it to get my scale factor. Our volume went from small to big. So when I do my division to get my scale factor, that's great. It's a number bigger than 1, but then I take the cubed root of it to get my scale factor. Okay? And that's it. Good job.